All right, 6.1, we're going to look at the law of cosines. And before we start, and I'll kind of say this a couple times as we go through this, is we're dealing with oblique triangles. And our definition for an oblique triangle is any triangle that's a non-right triangle. And I'm going to put this in red, and you should highlight this or put this in red as well. But because we're dealing with oblique triangles and non-right triangles, things like the Pythagorean theorem don't work. Things like SOHCAHTOA don't work because those are only true in right triangles. Now, yes, we're going to be using like sine, but we're going to show that we can, and the reason how we do that is by creating right triangles. So right off the bat, if we look at our law of sine, so we don't have the formula, but we can look at it. Anytime that you have a triangle, we want to mark the angles A, B, and C. We also want to mark the sides. Now the sides are specific. We're going to mark the sides as the one across from the angle, so A across from A, B across from B, and C across from B. Now it's conventional that we put uppercase letters for our angle measures or our angle names, and we put lowercase letters to depict a side. So we're going to look and kind of derive our law of sines. And the first thing that we do to show that this law of sines works, before we even say what it is we're going to draw a height in this triangle. And that's going to be the basis. Now, for why this is going to work, because we've just created two right triangles. So using that, let's describe things in terms of h. We threw this h in here, so let's use it. And what I know from here is I've got this angle A, and I can say using h that the sine of A is equal to h over b, opposite over hypotenuse. So if I look at angle B now, I can describe angle B the same way using h. Sine of B is h over A. Still the opposite length over the hypotenuse of this second right triangle. So now with a little figuring, because both of these, the sine of A and sine of B doesn't mean that they're going to be the same angle. A and B don't have to be the same side length. But what we know is h is always going to be the same. H will be the same in both of those statements. Sine of A equals h over B. That's the same h that we use in the second equation. Sine of B is h over A. So B times the sine of A is equal to h, but also A sine of B is equal to h. What does that do for us? What does that mean for us? It means that these two statements are equal because they both equal the same h. And now with a little figuring, and divide by A. And I'm going to divide by b on the other side. And the first part of our law of sines comes to light. We can write this as sine of a over a is equal to the sine of b over b. So really what we're saying with these two fractions, remember with fractions, we're just saying this ratio is true. So the ratio of the sine of a to the side length a is equal to the ratio of the sine of b to the side length b. So that's a little significant, and we could go through and show that it's true for the other side, but let's just write this out. This is the law of sines. Sine of a to a is equal to the sine of b to b is equal to the sine of c to c. Now it might look weird using two equal signs. We're just saying that all three are equal. So sine of a to a is equal to sine of c to c. Sine of c to c is equal to the sine of b, and sine of a of compared to a is equal to the sine of b to b. And if we flip all of these, the reciprocals are true as well. So I'm going to kind of put an or. A is to the sine of a is equal to b to the sine of b, as c is to the sine of c. So here's our law of sines. This is what we're going to be using today. Kind of a rule of thumb, what I like to look at is I like to use this one when I'm looking for solving for an angle. And you'll see why when we get into problems. And this one I like to use when we solve for a side.